Hello everyone. So in the first part of this lecture, we learned that enzyme speed up the rate of a reaction by lowering its activation energy. Okay, so in this part, I'll talk how enzyme do that. I mean, how enzyme lower the activation energy. So enzyme lower the reaction rate of a reaction. So why they do that? I mean, to do that, the enzyme need to interact with the reactant or the substrate. Okay, so from now I'll call the not the reactant, I'll call them substrate. Okay, so enzyme react with the substrate and then it's lower the activation energy. So do the whole enzyme, does the whole enzyme do that? No. In every enzyme, we are not talking about the ribozymes. Okay, so I mean those RNA enzyme, we're talking about the protein enzyme. So in every protein enzyme they have a specific area in it, a site in it, and this site is called the active site. Basically, active site is that site of a of an enzyme where the substrate come and bind with it. Okay, and this active site, it contains both the substrate binding site and also the catalysis site. Sometimes the binding site, and for some enzyme the binding site and the catalysis site is same. In some enzyme these are different. The binding site and catalytic site is different. Okay, but all are in the active site. Okay, so basically these active sites of enzyme, okay, they provide a unique environment. Okay, they provide all the environmental requirements where the activities to lower the activation of energy can occur. Okay, so that means this active site, this enzyme active site has some unique characteristics. They have some characteristics such as, how actually the active site of an enzyme is. It's a 3D cleft. Okay, three-dimensional cleft formed by groups coming from different parts of the enzyme. Okay, and the active site or sites are relatively small, and it has a unique microenvironment in it. Okay, and the substrate binds in the active site by multiple weak interactions. The substrate binds with the enzyme in the active site by multiple weak interactions. Okay, and we already know the specificity of this substrate enzyme binding depends on precise arrangement of the atoms of the enzyme. Okay, so when the atoms in the active sites are precisely arranged, then it will bind very specifically with its substrate. Okay, so anyway, so in a enzymatic reaction, okay, so what's the first step? The enzyme bind with the substrate come and bind with the enzyme. Okay, sorry, the substrate will come and will bind with the enzyme, and a complex between enzyme and substrate will form, and this complex is called ES complex. Okay, so when the enzyme will bind with, or the substrate will bind with enzyme, that means some interactions will happen. It will release some energy basically, and this energy will help to this energy will help the reaction to proceed faster. Okay, that means, and this energy is called binding energy. Okay, so the binding energy is the energy that is derived from enzyme substrate interaction. Okay, and it is denoted by del GB. Okay, binding energy, the substrate bind with the enzyme or interacts with the enzyme, and some energy is released. This energy is called binding energy, and this energy actually is a free energy. That means this energy can work. What kind of work? They can help the reaction to proceed faster. They help to bring down the activation energy, to lower the activation energy. Okay, so now think, as binding energy is released when substrate bind with the enzyme. So when the maximum binding energy will be released? When the substrate will bind with the enzyme very specifically. Okay, so far we know that the substrates are very specific with the energy. It's true, but it's not actually completely true. Okay, so not the original form of the substrate, Rather, a transient form of the substrate is more complement with the active site of the enzyme. Okay. So that means the full complement of enzyme substrate interaction is formed only when the substrate is in the transition state. So as I just said, not the original form of the substrate, rather a transform, a different form. And this form actually and substrate are in this form when they are in the transition state. So that means the transition state form of the substrate is most complement with the active side of the enzyme. So that means when the substrate are in their transition state form, they will optimally or maximally bind to the active site, and maximum binding energy will be released. Okay, and this binding energy contributes to the specificity and catalytic power of the enzyme. Okay, so I mean, so if a reaction wants to proceed, the reaction needs the activation energy, right? So somehow we have to provide the activation energy. The binding energy contributes in this activation energy. You know? Okay, so I mean the reaction, if a reaction wants to occur, it needs the activation energy. So binding energy can contribute here. Okay, so let's see. I mean, what is that? I mean, we are just saying that the the reactions, they need certain amount of energy, which we are calling activation energy, to proceed. So who actually contributes to this activation energy? Contributes to this activation energy means why the reactions actually, why the reactor need this certain amount of activation energy. Okay, there are several physical and thermodynamic factors who contribute to this activation energy. Okay, who make this energy barrier. Okay, and binding energy help to overcome these barriers. Okay, so now let's see what are those physical and thermodynamic factors who contribute to the activation energy or make the energy barrier. Okay, so there are several factors. The first, the entropy of molecules. Okay, the entropy, freedom of molecules in solution, which reduces the possibility that they will react together. If the entropy is high, so that means the molecules, they are moving freely. So if the molecules are moving freely, there is less chance they will interact with each other. Okay, so to interact them, okay, so to make sure that they will interact with each other, we have to decrease the entropy. So that means we have to provide some energy. So it will, and this energy, it will contribute to the activation energy. Okay, so then the solvation shell. We already know what is solvation shell, right? From the second lecture, the water lecture. Okay, so the solvation shell of hydrogen bonded water that surrounds and helps to stabilize most biomolecules in aqueous solution. Okay, suppose the hydrophobic molecule is in the water, so solvation layer or shell is there. So if a reaction need to occur, first this solvation layer need to be broken. So to do that, energy will be required. Again, it will contribute to the activation energy. Then the distortion of substrates that must occur in many reactions. I just said that in the last slide, the previous slide, that not the original form of the substrate, rather a changed form of the substrate, which we can call the distorted form of the substrate will maximally bind with the enzyme. So that means the substrate need to be distorted, and for this distortion, energy is required. Again, this will contribute to the activation energy. And finally, the need for proper alignment of catalytic functional groups on the enzyme. So now the substrate has bound with the enzyme active site. Okay, so now the enzyme will catalyze it. Okay, as the enzyme will do the catalysis, but to do that, in the functional group of the catalytic site of the enzymes need to be in proper alignment. Okay, and for this alignment, again some energy is required, which will contribute to the activation energy. Okay, so these are all the factors which contribute to the activation energy, and here's come the binding energy. The binding energy, they can be used to overcome this barrier. Okay, that means the binding energy can be used to overcome all these barriers. That is the entropy reduction, desolvation, breaking up the solvation shell, formation of weak bonds, and to make the substrate fit, to distort the substrate, thus it will fit with the enzyme. Okay, must complement it. Okay, so we heard that enzyme. Okay, we already talked a lot about like what enzyme do. They lower the activation energy. Okay, so but actually, how enzymes do it? I mean, how enzymes actually work? How enzymes actually lower the activation energy? To lower the activation energy, it needs some energy. So, what is the source of this energy? Okay, that means what is the source of the energy for the dramatic lowering of the activation energies for a specific reactions. Okay, I mean enzyme lower the activation of a specific reaction. So what is the source of the energy? Okay, so now I'll talk about the source of the energy. Which energy contribute to the which energy work to lower the activation energy. Okay, so first there are actually several ways. So first way, rearrangement of covalent bonds by rearranging the covalent bonds during an enzyme catalyzed reaction. Okay, and chemical reactions of many types take place between substrate and enzymes functional groups. Okay, a specific amino acid side chains, metal ions, coenzymes, etc. So when the this rearrangement of covalent bonds occur, so covalent bonds are broken down. So whenever and these are chemical bonds, right? So whenever these bonds break down, energy is released. Binding energy is released. Okay. So this energy can help to lower the activation energy. So this is one source. Another source of energy is covalent interactions between enzymes and substrates. Okay. Due to these interactions, binding energy is released, which lower the activation energy. Okay. By providing. Okay. Okay. Uh, then another source. Okay. So much of the energy which is required to lower activation energies is derived from weak non-covalent interactions between substrate and enzyme. Okay, so not only the covalent interactions, many weak non-covalent interactions between the substrate and enzyme occurs, and in fact, these non-covalent interactions provide most of the energy which is required to lower the activation energy. Okay. Okay, and again, and also these same non-covalent interactions are critical to the formation of complexes between proteins and small molecules, including enzyme substrates. Okay, okay, and again, these weak interactions are optimized in the reaction transition state, not in the original form or state of the substrate. Okay, this also this non-covalent interactions are maximum or optimum in the reaction transition state. Okay. Okay, and I already actually said this one. Enzyme active sites are not complementary to the substrates per se, but to the transition states through which substrate pass at are converted to products during an enzymatic reaction. That means when the substrates are in the transition state form, they are most complementary to the active side of the enzyme. Okay. And the next few slides, actually, you don't have to read these slides carefully. This actually in the next few slides is describe the scenarios. I mean that the not the original form of the substrate, the transform or distorted form of the substrate is more complementary with the active side. Okay, so if you look at this figure, say suppose this is the reaction. I mean the original substrate is a stick, and if it break down, the form is the products are formed. Okay, so that means for the formation of the products, this stick, this it need to be bent. Okay, so if it bent finally evenly, it will break down. Okay, so now I mean if we want to catalyze this reaction with enzyme, okay, then we'll use an enzyme. But actually this original form of this substrate is not perfect complementary to the active side of the enzyme. So rather, when this stick is bent like this, it will be in the perfect fit. Okay. So now, if we want to bend this one, it itself will require some energy, right? So if the reactions occur without, in absence of the enzyme, again, it need to be bent out. But in that case, we have to provide the energy which will bend it down. But in case of enzymatic reactions, okay, although this original shape, this stick is not perfect fit with the enzyme active site, but even they will do some interactions with the enzyme active sites, okay, and due to these interactions, some binding energy will be released, right? And this energy actually will work here. They will help. They will help the stick to be bent down. Okay, this energy which will be released from the interactions, they will help. Okay, they will contribute. To bend the stick. Okay, so once this stick is bent, that is the substrate is bent, it will be in the perfect fit with the activation site. It will maximize the interactions and it will maximize the release of the release of energy, and that energy will help for the catalysis, and eventually the product will be formed. Okay, so okay, that is how enzyme work. So okay, that's all for this lecture, that how enzyme works, how the enzyme lower the activation energy. Okay, see you in the next lecture. Till then, be safe. Thank you.